Yeah, now in this video, I'm going to discuss about this SP3d hybridization. I've already dealt with the other types of hybridization, that is SP2 and SP3 in my previous videos. Now let's deal with this SP3d hybridization and also this d orbital contraction, why PCl5 exists and why PH5 does not exist. And the whole chapter of this chemical bonding has been discussed on my YouTube channel, which has been pulled out from this degree first semester syllabus. And yeah, do like, share, and subscribe my channel if you like it. And the whole chapter has been the details of this description has been given on my under the description box below. Yes, when we come to this SP3D hybridization, just a second. Yes, when we look at this sp3d hybridization, we know that as the name 1s, 3p orbitals and 1d orbital, 1s orbital, 3p orbitals and 1d orbital will participate in the hybridization, resulting in the formation of 5 sp3d hybrid orbitals. So the number of hybrid orbitals which are formed are 5 of the type sp3d type. Yes, and and all these 5 hybrid orbitals which are formed here are identical in shape and degenerate. That means they're of the same energy and also the shape is same, consisting of one bigger lobe and one smaller lobe now. So which will be easy for the overlap to be formed. So I said this VBT is totally, the valence bond theory is totally based on the overlap of the valence atomic orbitals. So when this hybridization occur, the orbitals which are formed here, the hybrid orbitals will be able to overlap with the atoms easily, and the most effective overlap will be formed. And it will have the hybrid orbitals which are formed will have 20% of S character, 60% of P character, and 20% of D character. And these orbitals will arrange themselves in the space in such a way that there is a minimum repulsion. That means in this case it's trigonal bipyramidal. Yes, arranged in okay, yeah, trigonal bipyramidal shape. That means three of them in will be in one plane, where three bipyramidal, yes, and three orbitals will be arranged in one plane, and two other orbitals, one above and below the plane here, at right angles to each other. So this is called as looking like a pyramid. These three in one plane and above and below are like two pyramids. So trigonal bipyramidal in shape, and the angle in between them is, these are at 90 degrees to this plane, and the angle in between these three is around 120 degrees. There are two angles which are formed here, that is 90 and 120, and the shape of these is trigonal bipyramidal. Now let's see this with the help of an example here. For example, when we take this PCl5, we know that phosphorus in the ground state, it is atomic number is 15, so it has electronic configuration will be 1s2, 2s2, 2p6, 3s2, and 3p5. Yes. No, 3p3, right, 3p3. So 5 electrons in the outermost shell here, that is 2 in the s orbital and 3 in the p orbitals here. So now that it should form 5 bonds with 5 chlorine atoms. Now it has been explained that the excitation of an electron is possible from s to the d orbital, resulting in the formation of now 5 unpaired electrons totally in the excited state of this fluorine atom. So these 5 electrons in which are present in sp and d orbitals will hybridize together, resulting in the formation of 5 sp3d orbitals, which are identical in shape as I said and degenerate. And now these 5 orbitals, hybrid orbitals, will overlap with the p orbitals of this chlorine, resulting in the formation of PCl5 here. So this here it's depicted the formation of PCl5, where the hybrid orbitals are, the electrons in the hybrid orbitals are getting overlapped with the p electron of this chlorine atom, resulting in the formation of PCl5. So the Cl is 17, so it is 1s2, 2s2, 2p6, 3s2, and 3p5 here. So it's overlapping with one of the p electrons of this p orbitals of this chlorine atom. So that the phosphorus is now each of these sp3d hybrid orbitals is overlapping with the p orbital of this chlorine atom, resulting in the formation of PCl5 here. So there is a pairing up of the electrons which are occurring. There is a electrons with the opposite spin here, so resulting in the stable molecule. So when we look at the diagram of this can be easily explained. First, these are the P here central atom, which the five orbitals are arranged in trigonal bipyramidal model, so has to have the minimum repulsion, and these are sp3d hybrid orbitals of this fluorine. Each of this is overlapping with the 3p orbital of this chlorine, 1s2, 2s2, 2p6, and 3p2 and 3p5. So 3p5 means it has one unpaired electron here. So this electron, this opposite spin is pairing up with this electron in the hybridized orbital of this fluorine atom. Uh, so the five Cl atoms are getting paired up, resulting in the formation of this PCl5. This is the trigonal bipyramidal structure of PCl5, where the bond angles is 90 and 120. These are called as axial bonds, and these are called as equatorial bonds. So the hybridization and the structure of PCl5 can thus be explained based on this hybridization. But when you look at it, so for the hybrid orbitals to be formed, we know that the energy difference between the hybridizing orbitals should be very small. So for the S, P, and D, in this case of PCl5, as I said, it is SP3d hybridization. The energy difference should be very small. So according to this theory, what he said is the energy difference between the hybridizing orbitals should be small. But as we know that the d orbital size is more, so the energy is also more. So energy is directly proportional to the size here. So as the size is increasing, as the radius is increasing, size is increasing. So as the size increases, the energy is also more of the d orbitals. There is a vast difference in between the energies of sp and d. But how is it possible that the d orbital is participating in the hybridization in the formation of this PCl5? So in order to explain this, we can uh, get into this d orbital contraction. So let's understand what is this d orbital contraction now. So it can be explained based on three factors, the d orbital contraction. The first one is the charge on this central atom. Charge on this atom. That means, for example, when we are taking this PCl5, the charge P here is bonded to 5 Cl atoms here, right? So we know that the phosphorus is less electronegative when compared to that of the Cl. So as a result, the Cl will try to draw the electrons more towards it than its share. So the bonded pair of electrons are drawn more closer towards this chlorine atoms because of its higher electronegativity. As a result, this will get the partial negative charge and the phosphorus is going to get the partial positive charge. So because of this partial positive charge which is present on this central phosphorus atom, it will try to attract the electrons closer towards it. So it has 3s, 3p and 3d electrons. This is a nucleus of the phosphorate atom. So this will try to attract the electrons of this nucleus closer to it because of the partial positive charge which is present on it. As a result, this will contract the 3s orbitals, 3p orbitals, and 3d orbitals. But we know that 3d orbitals will contract more when compared to that of these 3s, p, and s orbitals. Because of this contraction of d orbital, this is called as d orbital contraction, the energy difference, the size is decreasing now. As the size decreases, as energy is directly proportional to the size, energy of these 3d orbitals is also decreasing. As a result, they are of compatible energy now. There is not much difference in between 3s, 3p, and 3d orbitals. So now these can participate in the hybridization very easily. Yes. So, and this effect is greatest for 3d orbitals, as I said, which is present in the outer orbital. So The size contraction, that's the d orbital contraction, is occurring as a result. The hybridization is possible in PCl5 because of the electronegativity difference in between this phosphorus and chlorine atoms. But when we come to this pH5, this does not exist. PCl is existing, which can be explained because of the electronegativity difference in between chlorine and phosphorus. As a result, this is going to get the partial positive and partial negative charge. Because of this positive charge on the phosphorus atom, it will try to attract the outer electrons more closer toward it, resulting in the d orbital contraction. As a result, the hybridization will occur between sp and d orbitals. But when we come to pH5, this contraction is not possible because the hydrogen is not electronegative when compared to that of this phosphorus atom. Yes, so pH5 does not exist, but PCl5 do exist, which can be explained on the based on this d orbital contraction. And there are two other factors also which will affect the size of the d orbital. Yes, and one more thing, when we come to this SF6, there is SP3d2 hybridization in this. Yes, I'm going to discuss this later on. So this sulfur, if there is only is SF6 formation, there are six fluorine atoms which are present around this sulfur atom. As a result, because of the presence of this highly electronegative fluorine atoms, which are six in number, there is a positive charge which is developed on this. As a result, there is a d orbital contraction, and d orbitals will contract and lowers its energy. So the hybridization is possible between sp and d orbitals. So the formation of this SF6 can be explained. There are two other factors which are affecting the size of the d orbital. That second is the d orbitals, the number of the electrons which are present in this d orbitals. For example, if you take this sulfur, if only one 3d orbital is occupied, the average radial distance is 2.3 angstroms. If there are two electrons in the 3d orbitals, when two 3d orbitals are occupied, that means there are two electrons which are present in it, the distance drops to 1.6 angstroms. And a third factor is contraction of this d orbital is also possible when pairing up of these electrons occur. That means the spin of the electrons, the coupling of the spin of the electrons occupying the different orbitals. So the three factors which are affecting the d orbital contraction is, first one is the charge on the central atom. Second one, the size of the orbitals is dependent upon is the number of the electrons which are present in the d orbitals, and third one is the spin of the electrons, that is the coupling. Yes. So so this is what is d orbital contraction. And when we come to this sp3d2 hybridization, as the name, one is 3p and 2d orbitals will participate in the hybridization. These orbitals resulting in the formation of six hybrid orbitals of the type sp3d2. So these six hybrid orbitals now will arrange in space in such a way there is a minimum repulsion, that is the shape of it is octahedral geometry with a bond angle of 90 degrees, so that there is a minimum repulsion in between these orbitals. So yes, these four are in one plane and these two are above and below the plane of the molecule. So this shape is called as an octahedral arrangement. Yes. And this can be explained with the help of an example here. For example, when we take this sulfur in the ground state, it has SF6, right? The formation of SF6 here can be explained based on this sp3d2 hybridization. The sulfur, its atomic number is 16, so its hybrid configuration will be 1s2, 2s2, 2p6, 3s2, and 3p4. But so only four electrons here which is present in the outermost shell, but it should form bonding with six other fluorine atoms. So in order to explain that, the two electrons from this s and p orbitals getting excited to the 3d orbitals, resulting in the formation of six unpaired electrons in the valence shell of this, that is the third shell. Now, these six electrons, these six orbitals will undergo the hybridization, that is 1s, 3p, and 2d orbitals, resulting in the formation of sp3d2 orbitals, which are six in number, which are degenerate, having the same energy and also same shape, and this will overlap with the p orbitals of this fluorine, each of which will overlap with one of the p orbitals of this fluorine, resulting in the formation of sf6 molecule, sf6. Yes, this fluorine, as I said, is 9 atomic number, so electronic configuration will be 1s2, 2s2, 2p6, yeah, 2p5 here. So there's one unpaired electron which is present in the 2p orbitals of this. Each of this will overlap with one of the hybrid orbitals of this sulfur, resulting in the formation of SF6 molecule with the octahedral geometry and having a bond angle of 90 degrees. Yes, so that's the hybridization in SF6 can be explained. When we come to this SP3d3 hybridization, in this, as the name suggests again, 1s, 3p orbitals and 3d orbitals will participate in the hybridization, resulting in the formation of 7 sp3d3 hybrid orbitals, which are 7 in number. All of them are equal in shape, degenerate, having the same energy, and arranged in such a way that the five of these orbitals are arranged in one plane, that is pentagonal, and two of them above and below the plane. So it is pentagonal bipyramidal. The geometry of this is pentagonal bipyramidal and making an angle of 72 degrees. Yes, so this is pentagonal bipyramidal geometry, pentagonal bipyramidal, because above and below the plane this is arranged, these two orbitals. So it is like pentagonal, one plane, and above the plane one pyramid, and below the plane one pyramid. So it is pentagonal bipyramidal geometry. And for example, when we take here, I have 7 here. So I is of halogen, so 17th group element, so 7 high electrons, its outermost shell, this one. So it has 7 electrons in the outermost shell. So the excitation will take place from s and p orbitals to the d orbitals, resulting in the formation of 7 unpaired electrons here after the excitation. So all of them will undergo the hybridization here. One is 3p and 3d orbitals, resulting in the formation of sp3d3 hybrid orbitals, which are 7 in number, and all of them will overlap with the p orbitals of this fluorine. Fluorine is 9, right? So 1s2, 2s2, and 2p5. So each of these hybrid orbitals will overlap with the p orbital of this fluorine, and resulting in the formation of this pentagonal bipyramidal geometry. So thus the formation of this IF7 can be explained. Right. So when we look at this shapes here, so for sp hybridization, it is linear, and for sp2 hybridization, it is trigonal planar where the angle is 120. And for sp3 hybridization, the shape is tetrahedral where the angle is 109.5. And when the hybridization is sp3d, the shape is trigonal bipyramidal with the bond angles of 120 and 90. And with the sp3d2 hybridization, the bond angle is 90 degrees with the shape of octahedral geometry. Yes, for this, I have example is BeCl2. Here it is BF3, and here it is CH4, PCl5, and SF6. So for SP3d3 also I've explained, this is example is IF7, where it is pentagonal bipyramidal shape and geometry. Pentagonal bipyramidal, yes. So this helps the hybridization here. So, and the shapes of carbon dioxide and SO3 can and SO2. I'll deal them in my next video. Yes.